I'm Dr. Bino. In Artificial Intelligence and Machine Learning Fundamental Subject, the fifth unit is Unsupervised Learning. This unit consists of the following topics: unsupervised learning, principal component analysis, neural network, fixed weight competitiveness, coherent self organizing feature maps, clustering, definition, types of clustering, hierarchical clustering algorithms, and K means algorithm. First, we will see what is meant by unsupervised learning. Unsupervised learning in machine learning is a type of learning where the algorithm is trained on unlabeled data. Unlike supervised learning, unsupervised learning only has input features, and the goal is to find hidden patterns, structures, or relationship in the data. This diagram represents the unsupervised learn how the unsupervised learning algorithm works. Here, the input is nothing but the data is uh, without labeling. Based upon the learning algorithm, it should identify the patterns and it should categorize the particular type of either shape or color or whatever may be. In unsupervised learning, where the algorithm learns from unlabeled data without any predefined output or target variables. The input raw data is the unlabeled data. Here, what are the steps followed means first interpretation, the suitable algorithm is applied over that, then processing. Based upon the processing from the unlabeled raw data, the output is categorized. We already know the machine learning consists of three categories: supervised, unsupervised, and reinforcement learning. The unsupervised learning has the model training with unlabeled data. The main classification is clustering. The clustering consists of K means clustering, DBS, CAN, hierarchical clustering, principal component analysis, as well as association. What are the key characteristics of unsupervised learning means it works with unlabeled data, which is nothing but no predefined categories or outcomes. The algorithm learns the structure or distribution of data. This is useful for exploratory analysis when you don't know the categories beforehand, which is normally used for dimensionality reduction, clustering, and anomaly detection. What are the types of unsupervised learning? First type is clustering. Clustering is nothing but grouping data points into clusters based on similarity. The commonly used algorithms are K-means algorithm, hierarchical clustering, and DBS-CAN. The example for the clustering is customer segmentation in marketing. Second type of unsupervised learning is associative rule learning. Here, finding the relationship or correlation between variables. The significant algorithms used in this rule learning is a priori FB growth. Example application for this particular learning algorithm is market basket analysis. That is people who normally buy milk along with bread. The third one is dimensionality reduction, reducing the number of features while preserving information. Principal component analysis, TSC, autoencoders or the popular algorithms comes under this category. Compressing images for faster computation is the example comes under this particular dimensionality reduction learning algorithm. Fourth one is anomaly and outlier detection, which is used to identify the unusual patterns. Normal algorithms are isolation forest, one class SPM. A fraud detection in credit card transaction is the example for this anomaly detection. Applications of unsupervised learning. Customer segmentation in business or marketing, recommendation system for Netflix and Amazon, fraud detection in banking, genetic clustering in biology, social network analysis, image compression, and feature extraction. Then we will see principal component analysis, simply called as PCA. It is a dimensionality reduction technique normally used in machine learning, statistics, and data analysis. The goal of PCA is to transform high dimensional data into lower dimensional form while preserving the variability as possible. This is achieved by identifying the principal components, that is major components that explains the most variance in the data. PCA is a statistical method for dimensional reduction that transforms a dataset's original variables into smaller set of new uncorrelated variables called principal components. These principal components are ordered by the amount of variance they capture from the original data, with the first few components representing the most significant information, making complex data set easier to visualize, understand, and process. PCA finds applications in exploratory data analysis, data visualization, and data pre-processing across various scientific fields. This diagram represents how the principal components will be working. The key components in the principal components are: first step is dimensionality reduction. PCA reduces the number of features in your data set without losing too much information. This helps to improve the performance of the machine learning models, speed up computation, and aid in visualization. Second step is variance. PCA finds directions that maximizes the variance in the data set. It identifies the axis along which the data is most spread out. Third step is principal component. These are the new axes, that is directions that PCA uses to project the data. The first principal component accounts for the largest variance. The second principal component is orthogonal to the first and explains the second largest variance, and so on. Fourth step is orthogonality. The principal components are orthogonal, that is perpendicular to each other. This means each principal component captures a unique aspect of the data's visibility. Steps used for the PCA. First step, standardize the data. PCA is affected by the scale of data. It's important to standardize the data so that each feature contributes equally. This involves subtracting the mean and dividing by the standard deviation for each feature. Second step is compute the covariance matrix. The covariance matrix shows how features of the data are correlated with each other. If the features are highly correlated, PCA can reduce the dimensionality without losing much information. Third step is compute eigenvalues and eigenvectors. Eigenvectors represents the direction of new axis, that is the principal component, and the eigenvalues give the amount of variance each principal component explains. The higher the eigenvalue, the more significant the principal component. Next step is sort the eigenvalues and eigenvectors. The eigenvectors are sorted by their corresponding eigenvalues in descending order. The first few eigenvectors will explain most of the variance in the data. Fifth step is select principal components. Decide how many components you want to keep. Often you select enough components to capture a high percentage of variance, normally 95%. Sixth step is transform the data. Project the original data onto selected principal components to get the transformed data. This is the reduced dimensional representation of your dataset. Now we will see some of the advantages of PCA. It reduces the complexity, the performance is getting improved, then data visualization is also getting improved. Some limitations are also there in PCA. First one is linear assumption, second one interpretability, then sensitive to scaling. And the next topic is coherent self-organizing feature maps, that is SOM. It is a type of unsupervised neural network that projects high dimensional data into lower dimensional while preserving the topological relationship of the input data. It takes complex data and organizes it into 2D map so that similar data points end up closer together. SOMs, also known as coherent maps, are a type of unsupervised neural network used for dimensionality reduction, clustering, and visualization of high dimensional data. This is were introduced by Theo Coherent in 1980s. Coherent SOM is a 2D neural map where neurons compete and learn to represent clusters of similar input data. This is widely used in clustering, visualization, and dimensionality reduction in unsupervised learning. Some of the key features of SOM are: it is unsupervised learning, as there is no labels are needed. Then use competitive learning, only one winning neuron updates per input. Preserves data topology, that is neighbors in input space remain neighbors on the map. Useful for visualization and clustering of high dimensional data. The architecture of SOM. First one, input layer, that is represents the features of the data. That is normally the input vector is represented by x1, x2 up to xn. A coherent layer, 2D grid of neurons. Each neuron has a weight vector of the same dimension as the input. These neurons are arranged in a grid type, that is in rectangular or hexagonal shape. The architecture of a coherent SOM is represented in this diagram. Now we will see the working of SOM algorithm. First step, initialize the weights randomly for each neuron. Input a vector from the dataset. Find the best matching unit, that is simply represented as BMU. Compute distance between input vector and all neuron weight vectors. The neuron with minimum distance, that is best matching unit, is the winner. Fourth step is update the BMU and its neighbors. Adjust the weight vectors to move closer to the input vector. Neighbors in the grid are also getting updated. The formula used for SOM is W of t plus 1 is equal to W of t plus alpha of t in the HBMU of t in the x of W of t. Alpha of t is the learning rate, HBMU of t is the neighborhood function, x is input vector. The fifth step is repeat many iterations, weights self-organize into 2D maps. The detailed diagram of SOM is represented in this illustration. Example. Now we will see one example. Imagine a customer data with age, income, and spending habits. SOM maps customers into 2D grid. Customers with similar behavior, that is young and high spenders, appear close to each other on the map. Applications of SOM, which is normally used in data clustering and visualization, for marker segmentation and bioinformatics, image compression, speech recognition, anomaly detection, and exploring high dimensional data in finance and medicine, etc. Some of the advantages of coherent SOM are: preserves the topological properties of the input space, good for visualizing complex high dimensional data, because it is unsupervised, no need of labeling the dataset is needed. Limitations: a choice of map size and learning parameters affects the quality, can be slow to converge, sometimes difficult to interpret the resulting map in very high dimensions. Thank you.